When a million people open the same Instagram profile at the exact same second, or when 10 million users watch the same viral YouTube video, why doesn't the database just melt? The secret is those systems are not hitting the database every time, they cache. If you remember from our past phase, databases are powerful, but they're not designed to handle infinite reads per second directly. Today we unlock the real performance layer of modern systems, and that is caching. But before we can look at the advanced strategies, we need to understand the fundamental physics of why caching works. It all starts with the inherent pain of data retrieval. Imagine this, a user opens your app, you fetch their profile, your server hits the database reads from the disk. Here's the problem, disk is slow, network is slower. Now multiply that by 500,000 users per second. Your database becomes the bottleneck. Even worse, most of those reads are repetitive. It's just coming from the same profile, the same video, and the same homepage. Why are we reading the same data again and again from the disk? It is inefficient. To fix this, we need a way to store that frequently accessed data in a place that's much closer to the CPU and significantly faster than any disk could ever be. Instead of asking the database every time, we store frequently accessed data in memory. Memory is about 100 times faster than disk. The architecture changes, like if data exists in the cache, it returns instantly, and that's called a cache hit. If not, it's called a cache miss. And we fetch that cache miss from the database, store it in the cache for the next time, and return it. This drastically reduces the database load, latency, and infrastructure cost. But storing it in a cache is easier said than done. Depending on your system needs, there are three distinct strategies for how and when that data actually gets saved. And the first one is actually the industry standard. This is the pattern used by most web applications. It's called cache aside or lazy loading. Here, application checks cache. If found, it returns it. If not, it fetches from the database, stores it in cache, and then returns it. We call it lazy because we only cache what users actually request for, and it is simple and the database remains the source of truth. But the first request is always slow, and there is always a risk of stale data. If you remember only one pattern, you gotta remember this one. But what if your application is write heavy? What if you want to ensure that your cache is always perfectly in sync with your source of truth? Now imagine a user updates their profile. With write through, we write to the database and immediately update the cache. They stay perfectly in sync. The pro is your cache is always fresh, no stale reads, but the con is it has slower writes and higher latency during updates. This is your go to when consistency is a top priority. But what if you need the absolute maximum write speed possible? What if you're willing to gamble a little bit of safety for extreme performance? That's where things get dangerous and fast. And for that, we got to use a write back pattern. Now let's optimize for raw speed. With the write back, you write only to the cache. The cache then asynchronously writes to the database later on. This makes writes extremely fast. It's perfect for high throughput systems like analytics counters or gaming leaderboards. The trade-off is if the cache crashes before it writes to the database, you lose the data. You're trading consistency for extreme performance. But here's a problem with memory. It's expensive and limited. You can't store data there forever or you'll run out of space. To solve this, we give our data an expiration date. Caches cannot store data forever. When we attach an expiry time called TTL, for example, a profile is cached for 10 minutes, after that it's automatically removed. This is critical for session tokens, news feeds, and trending content. TTL prevents stale data from living forever in your expensive RAM. But what happens if cache fills up before the TTL expires? When space is gone and new data needs to come in, the system has to make a tough choice about who to kick out. And that's where we come to the eviction policies. So when memory is full, something must go. We have three methods for that. One is LRU, that is least recently used. So here we remove the item that hasn't been used recently. This is practical and very common. And the next one is the LFU, that is least frequently used. And here we remove the least accessed item, and it's good for long-term popularity. And the third method is FIFO, that is first in, first out. Simple but not very smart. So here's an interview tip. If you aren't sure which eviction policy to be used, just say LRU because it is the standard for a reason. Now that we know how to manage the data, we need to pick the right engine to run it. In the industry, two names dominate the land space. So one is Redis and another one is Memcached. Redis is powerful. It supports multiple data structures, persistence and replication. Use it for rate limiting, session storage and leaderboards. While Memcached is ultra simple and lightweight, it's a pure key value store with no persistence. If you need advanced features, pick Redis. If you need simple lightweight speed, pick Memcached. But even with the best tools, you eventually run into a single most frustrating problem in engineering. It's the reason profile pictures don't update and news feeds feel broken. So that is the cache invalidation. So there are only two hard things in computer science. One is naming things and other is cache invalidation and off by one errors. Why is invalidation so hard? Because when data changes, your cache might still hold the old version and that's bad UX. We balance performance versus freshness versus complexity, and that's where real system design comes in. So invalidation fixes the data, but what about the distance? If your server is in the US and the user is in India, the speed of flight becomes your new bottleneck. So that's why we use CDN and edge caching. Let's scale globally. If your server is in the US, why should a user in India wait 300 milliseconds for latency? CDNs, that is content delivery networks, store static content like images, videos, or JavaScript files closer to users. So this reduces latency and bandwidth costs. This is how Netflix and YouTube serve billions. Edge caching makes the internet feel instant. So we have seen the logic, the strategies, the tools, and the global scale. Let's look at how all these pieces fit together in a final production ready architecture. A modern scalable system looks like a user, then CDN, then load balancer, app servers, Redis cache, and database. Without caching, your system cannot scale. Databases are the foundation, but caching is the speed. So today we have covered why caching is necessary, the patterns like cache aside, tools like Redis, and the power of CDNs. I'll see you in the next one. Thank you.